So hi everyone. Today I'll be telling you about some work on differentially private sampling from distributions. This is joint work with Sofia Rozhodnikova, Adam Smith, and Marika Swanberg. Marika is here in the audience. We're all from Boston University. And so just to give you an overview of the structure of this talk, I'll start by introducing the problem we're going to be looking at, telling you about our results and the overview of techniques that we use to get them. And then I'll be explaining one upper bound and one lower bound in more detail. Okay, so in this work, we define this new problem called private sampling. So what are we given in this problem? We're given n records that are sampled IID from a distribution P that's from some specified class of distribution C. So C sort of corresponds to some prior knowledge you have about the distribution. Okay. And we think of these n records as individuals' data, basically, in this setting. And the goal of the sampler is to privately generate a single sample from a distribution Q that is close to P. So we want to generate a single sample, and we want that this sample has some distribution Q which is close to P. And the output distribution Q of the algorithm will take randomness from two sources. One is the selection of the data set from the population distribution, and the other is just the coins of the algorithm. And what do we mean by privately generate one sample? We just want the algorithm to be differentially private with respect to the input records that it uses. So I want to contrast this with the goal of private estimation. So in private estimation, you also have a class of distributions. But instead of producing a simple sample, you want to produce a description of a distribution, an entire description of a distribution that is close to the source distribution. And so what do you mean by description of a distribution? So if you consider the class of Bernoulli distributions, they're completely specified by the probability of outputting 1. And so you want to estimate that probability. So that's what learning would be. And for sampling, you just want to output a single sample, either a 0 or a 1. So that's just to contrast with the problem you guys may know. Okay, so we've said these words close to P for a while. So what do we mean more technically about close to a distribution? And here's our accuracy definition. We say a sampling algorithm A is alpha accurate in a class C of distributions for data sets of size n. If for all fixed distributions, population distributions P in the class, the output distribution Q of the algorithm and this distribution P are close in total variation distance, and we use the parameter alpha to capture this. Okay, so that's roughly what the problem is. So to give you some context about this problem and just so that you can situate yourselves, it's easy to see that if we didn't have concerns about privacy, sampling is trivial because we can just output the first record in the clear. And since the records are all sampled from the population distribution, this is a 0 accurate algorithm or a 0 error algorithm. 0 accurate feels weird, but yeah. Okay. But we can't do this with privacy because you can't just output the first record in the clear. That's not differentially private. So this problem is non-trivial in the private setting. And the second thing I want to point out is that this problem is sort of easier than private distribution learning, which is if you can privately generate a description of a distribution that's close to your population distribution P, then you can just sample from it, and that's like differentially private by post-processing. And what this means is that lower bounds in private sampling are lower bounds in private learning. Okay. So why study this problem at all? So our first goal was to sort of abstract the goal of privately generating a small amount of plausible data whose distributional property sort of matched the population distribution. And so the other thing we wanted to study is like what gains can we sort of get by relaxing the goals of private distribution estimation. We saw that this problem is a little easier than private distribution estimation. So maybe it's you can do things that are that save you on sample complexity, for example. And finally, it turns out that, and we'll talk about this later, that lower bound techniques that are used for private estimation don't directly work for this problem. And so studying this sort of gives us new insights into the challenges posed by differential privacy for simple statistical problems. Okay, so to give you a summary of the main contributions of this work, so we formulated this problem of private sampling that, to the best of our knowledge, has not been studied before. We gave tight bounds for several sort of simple classes of distributions, and we sort of related the sample complexity of different tasks. Specifically, we were interested in relating sample complexities between private estimation and private sampling. And so we found some interesting results. For some parameter settings, we found that the sample complexity of private sampling was basically equivalent to the sample complexity of private learning, even though at first glance it may seem that private sampling is easier since you only need to generate one sample from the distribution. But we found that for other parameter settings and other classes, private sampling was indeed easier, as this intuition may lead you to believe. And finally, for some distribution classes, we found that to the extent that private learning is harder than non-private learning, that extra hardness is completely explained by the hardness of private sampling. Okay, so this is just an overview of our main results. And to give you a sense of what type of related work was done. So what really inspired this idea was there was this work on sample amplification. So non-privately, the goal is to generate m greater than n IID observations when you're only given a sample of size n. So you want to sort of amplify your data set. And this was studied in this work by Axelrod, Garg, Sharan, and Valiant. And there's also been work on distributed sampling. So in this problem, each user is given one sample from a distribution. But they're restricted in terms of how many bits they can communicate to each other, and their goal is to work together with this restricted communication to produce a single sample. This looks kind of like the local model, and this is work of Acharya, Kannan, and Tyagi. Like we use techniques from and compare our bounds to like a host of work on private and non-private learning tasks, boundless literature on this now. And some of our upper bounds show that sampling actually allows you to get some privacy for free in some settings, and similar ideas were used in Bayesian inference. So there's a line of work on that. And finally, this looks like a synthetic data problem, and there's like a lot of work on synthetic data. We've just put one reference on there, but there's a lot of work on this at this point. Okay, so now I'll tell you about results and overview of techniques, but if anybody has some questions just about the setup, happy to take them. Okay. So to tell you about our results, so in this work we studied epsilon delta dp sampling, and so we compared it to two baselines. So one is just non-private learning, where you're just interested in learning the class of distributions with no concerns of privacy, and the other is epsilon delta dp learning of distributions. And the first class is really simple. We just started with Bernoulli distributions, and it's well known, at least 100 years now, that the non-private learning sample complexity of this task is like 1 over alpha squared for alpha accurate learning. And the cost of privacy, the extra term that you need for private learning, is this 1 over alpha epsilon term. And in our work, we found that this was completely explained by the cost of private sampling. So sample complexity of alpha accurate private sampling for Bernoulli distributions is 1 over alpha epsilon, where epsilon is a privacy parameter. And then we considered various generalizations of Bernoulli distributions. So first, we just considered discrete distributions with any finite support, supported on k elements. So that notation there, the square brackets with k, just means 1, 2, 3, so on till k, just a discrete set. And we found that, I mean, it's well known that non-private learning scales linearly in k and inverse linearly in alpha squared. And the privacy term for differentially private learning is this k over alpha epsilon term. And we found that this is exactly the sample complexity of private sampling. This again, this k over alpha epsilon term. And then we considered a different generalization of Bernoulli distributions. We considered products of d Bernoulli distributions. So first we considered arbitrary product distributions, and then we considered product distributions where the biases of each of the Bernoullis is restricted to lie in some interval 1 over 3, 2 over 3. You may say this looks a little artificial, but we'll explain why we thought about this class. And so for general product distributions, we found similar results. Things just scale linearly with d and behave similarly to previous settings. But for these product distributions of Bernoullis with bounded biases, we found something interesting. So in the learning setting, these are actually the hard instances. So you can show that the same sample complexities apply for this class. So the sample complexity of non-private learning of this class of product distributions with bounded bias is still d over alpha squared, and for epsilon delta dp learning, it's still d over alpha squared plus d over alpha epsilon. But interestingly, we found that while this was the regime where learning is the hardest, it was actually much easier for private samplers. So if you look at our upper bound there, the sample complexity of epsilon delta dp sampling for alpha accurate epsilon delta dp sampling for this class scales as square root of d as opposed to linearly in d. And the dependency on alpha is log 1 over alpha as opposed to 1 over alpha squared. And this is just an additive term as well. So significantly different. And we also have a lower bound of square root of d. You can add epsilon in there, but just for simplicity. And we see that for a bunch of our distribution classes, it seems like the sample complexity of private learning is equal to the sample complexity of non-private learning plus the sample complexity of private sampling. We don't know if this is a coincidence or not, but thought it was an observation that was worth pointing out, at least for these classes. Okay, so that's our results. Does anybody have any questions about these results before I tell you give you a high-level overview of our techniques. Hassan, yes. Because you'd have to produce like lots of samples, so that would give you like you'd have to like independently do this over and over again. Yes, this is just for a single sample. All of this is for a single sample. It can be extended for a constant number of samples, but once you're interested in parameters like your samples, yeah, okay, cool. So what are our main techniques? So for upper bounds, we show that you can exploit the randomness of sampling to get some additional privacy. This is how we got our improved sampler for product distributions with bounded bias. And for general product distributions of Bernoulli's, we use this recursive private preconditioning technique, which was introduced in previous work by Kamath, Lee, Singhal, and Ullman in the context of private distribution estimation of products of the Bernoulli's. So this is just to get the right sample, like the right dependence on the dimension D. And it turns out we also need new lower bound techniques. So what does a typical proof structure of a lower bound look like for private learning of distributions? You pick some discrete set of distributions that satisfy some condition. They're close in total variation distance, but far in some other metric. And then you use these tools like the Cam's method or Fano's inequality, all of these classical methods. And you argue that if you can learn the distribution, then you can identify the distribution from the set, and that violates some privacy condition. So this is the typical structure of what a lower bound would look like. But what I want to point out is that a single sample from the distribution cannot identify the distribution. And so this general recipe doesn't work for private sampling. To get lower bounds for private sampling, and so we have to try something different. And so two of our proofs use the following approach. We show that if you want an accurate sampler, then you have to output an element in the support of the distribution. And it turns out that even this task is hard for differential privacy. And that's the general framework of our lower bounds. And so the details sort of vary by the class. For discrete distributions with support size k, we use a custom argument that's based on group privacy and a bunch of other things. For product distributions, we actually reduce from sampling from k-re distributions to sampling from products of Bernoulli's. And for the case where we have product distributions with bounded bias, we reduce from another statistical problem, that of estimating one-way marginals, for those of you who know about that problem. And lower bound for that was previously proven by work by Mark Ban, John Ullman, and Salil Rajan. Okay, so this is just a high-level overview of our techniques. It's okay if all of the words on the slide don't make sense. Okay, so first to tell you about our upper bound and how it works. So we're going to consider a Bernoulli with bounded bias. We're not going to think about the dimension D. We're just going to set the dimension D to be 1. So your input is just going to be n independent samples from a Bernoulli with parameter p, where we restrict p to be between 1 by 3 and 2 by 3. And we want the output to just be a single sample, which is distributed roughly correctly. Okay. And what I'll claim about this algorithm is that in order to ensure privacy, we don't have to do any explicit noise addition, which is how we get our improvement. Okay, so the first step is just take the sample mean of the data set. Then you clip to this interval 1/4, 3/4. So what do you mean by clipping? So if the sample mean is smaller than 1/4, you set it to 1/4. If it's bigger than 3/4, you set it to 3/4. Otherwise, you just leave it untouched. You can call it truncation. There are lots of other synonyms that are used as well. And the specific 1/3/4 are not important. We just need that the interval is larger than 1/3, 2/3. And finally, you just use this as your bias estimate and just release a sample from this distribution. And so the claim is that this is epsilon 0 differentially private when n is sufficiently large. This condition on n is not particularly important. If the sample size is too small, just ignore it and output something canonical, and you're still private in that setting. So this is only interesting when n is large. Okay. So I'll prove this for you so you can attack me. So there are two outputs of the algorithm. It could output either 1 or 0. So without loss of generality, just consider the output 1. And so by definition of the algorithm, the probability that the output 1 is exactly this clipped mean p tilde. In step 2, you can see that over there. So now consider two neighboring data sets, x and x prime, as shown in the image. And first consider step 1 when the algorithm is executed on these two data sets. So you'll see that the sample means differ by at most 1/n. It's like classic sensitivity analysis. All of the entries are either 0 or 1, and so sample mean can only differ by 1/n. And it turns out that clipping can't really change this. If you think about it for a second, you'll see that clipping, the clipped means will also differ by at most 1 over n. And now we just need to do some math, so bear with me, we'll go through the inequality slowly. So basically these two bullets correspond to that first inequality. We just say that p tilde prime, which is p tilde on the one of the neighboring data sets, is within 1 over n of the clipped mean of the other one. And now we use the fact that we clip to the interval 1 over 4 comma 3 over 4. 1 is less than 4 p tilde in this setting, and so we get the second inequality, right? And now we just do some math. We take this p tilde common, and so you get 1 plus 4 over n. And now you just use a Taylor series approximation. This 1 plus t is less than or equal to e to the power t. So this looks like p tilde times e to the power 4 over n. And if n is sufficiently large, this is less than or equal to p tilde times e to the epsilon. So what have we shown? We've shown that the probability that we output 1, the ratio of those probabilities on two neighboring data sets is bounded by this e to the epsilon. And there's nothing special about 1. You can do this for 0 as well. And so that proves epsilon dp, since it's sufficient to consider pointwise outputs for epsilon dp. Any questions about this proof? Okay, cool. Yeah. So I'm not going to give you an accuracy proof, but you can show that this algorithm is alpha accurate when n is larger than log 1 over alpha. And so if you combine these two things, you get a differentially private and accurate algorithm as long as n is like roughly 1 over epsilon plus log 1 over alpha. It's really the maximum of the two, but that's like sort of equivalent to the sum. Yes.
So quick question about privacy. How easy it is to extend it to beyond 1/3, 2/3, or what's the dependence on the boundary?
Yeah, I think you can probably think about like epsilon comma 1 minus epsilon or something like that. I think yeah, something like that.
And it's like the sample complex is 1 over the bias? Or?
Yes, I think that's roughly right.
Okay.
To piggyback on that question, earlier you kind of brought up 1/3, 2/3, and 1/4, 3/4. I didn't realize where these 1, 2, 3, 4 numbers came from.
Yeah, so the numbers aren't particularly important. So 1/3 comma 2/3 comes up in accuracy, and like I said, it's just important. So we use the fact that we clip to the interval 1/4 comma 3/4 here, but like the numbers aren't important. It's just important that the interval is larger than the interval that the bias is restricted to be in.
I guess Stephen's question is they could be anything.
Yeah, as long as it's larger, you should be fine. Yeah.
But the n needs to be.
The n needs to be proportionately. Yeah, the n needs to be proportionately larger to get that last inequality to work, basically. Yeah.
Thank you.
Yeah. Okay. So just to contrast this with the sample complexity of alpha accurate private learning for this class, it's equal to 1 over alpha epsilon plus 1 over alpha squared, and you can see that the dependence on alpha is significantly better. And basically, if you have, instead of one Bernoulli, if you have products of d Bernoullis, you can actually just naively apply composition of pure differential privacy, and things will scale as square root of d. So that's where you get this bound. Okay, so that was the upper bound, and now I'll tell you about our lower bound. So I'm going to tell you about our Bernoulli product lower bound. So the theorem is simple. Every epsilon delta differentially private sampler that's alpha accurate in the class of products of d Bernoulli distribution requires data sets of size omega of d over alpha epsilon. So one of the reasons I like this lower bound is that it's very different from the way you prove lower bounds for private learning. So the lower bounds for private learning for this task use connections to fingerprinting codes. But for those of you who know what that is, but in this talk we actually we take a reductive approach. So we reduce from accurate private sampling for distributions with finite support, discrete distributions with support size k, and we reduce that to accurate private sampling from products of k Bernoulli distributions. So just because I don't want to say distributions with support size k over and over again, I'm going to call it C sub k, and I hope you'll forgive me. Okay, so just to pictorially represent what this idea looks like, so we want to construct a private sampler A for this class C sub k. We have a data set that's sampled from this distribution, and we want to produce a single sample from this data set sampled from some p, some distribution p in this class, and we want to produce a single sample from this distribution. And we have accessed, so when I say product distribution, henceforth I'm only talking about products of Bernoullis. But yeah, so let's say we have a private product sampler, takes a product data set and gives you a single sample from a product of product distribution of d Bernoullis. So to get this reduction to work, we need to do some type of language translation because the data universes we're using are very different. So the sampler for C sub k takes distributions with universe of k elements, whereas the product sampler works with data universes which are like d binary attributes. So the data universes are very different and some type of language transformation needs to happen. That's essentially what we do in our reduction. So we have a dataset transformation algorithm that takes this dataset sampled from P and converts it to a product dataset. And so now we can apply our private product sampler. We get a sample and then we just like translate back. So basically it's just a like both are translations. Okay, so this is like the high level overview. I lied to you a little bit, but only for your own good. Things don't end up quite so clean in general, so we need to reduce from a slightly related task, but for the purposes of this talk, just ignore that distinction. It's just for some annoying technical reason. Okay, so I won't have time to tell you about both of these language transformation algorithms, like as I like to call them, but I'll tell you about this dataset transformation algorithm for the remainder of this talk. Okay, so let's zoom in on it. So here's the lemma, which is again a slight lie. There exists a dataset transformation procedure that transforms n samples from any distribution P in C sub k to n samples from a product distribution of Bernoullis. That's the main theorem. Okay, so we're going to build up to proving this. So our first attempt is going to be just something called one-hot encoding in machine learning for those of you who know it. Also okay, whatever. I think it's easiest to explain this with an example. So let's say your data universe is 5 and you have some distribution over this data universe. And let's say your data set that was drawn looks something like this. So it's like 1, 4, 3, 3, 4. This is some plausible data set. So one-hot encoding just means take every data element and replace it with an indicator vector, which is a 1, which has a 1 in the attribute index of that element and zeros everywhere else. So for this data set, if you apply one-hot encoding, it looks something like this. So the first element is a 1, so you put a 1 in attribute 1 and zeros everywhere else. The second element is a 4, so you put a 1 in attribute 4 and zeros everywhere else, and you just do this for the entire data set. Really simple. So at least syntactically, this looks like 5 binary attributes. So syntactically, it looks closer to a product distribution. So we were just like, we hope this is sampled from a product distribution. But spoiler alert, it's not. Because every data point has exactly a single 1, right? Which means for a data entry, if you know that an attribute has a 1, you know that every other attribute is a 0. So there is a correlation between the attributes. So it's not a product distribution. And so this hope is dashed. So what's our goal? So we want to somehow get this to work and we want to make the attributes independent. And so our key idea is the following. So we make the following observation. So when you do one-hot encoding, observe that the number of ones in an attribute is the number of times that element occurs in the input data set. So because we only put a 1 in an attribute when the corresponding element occurs in the input data set, otherwise it's a 0 in one-hot encoding, right? And what this means is that if we can make the element counts in the input independent, then the number of ones in each attribute will be independent, which means the marginal distributions of the columns will be independent. So that's the main idea of our algorithm. Okay, so this is the goal. And essentially, we use one-hot encoding plus this technique called Poissonization, which some of you may have heard of. So this is a technique that's used in randomized algorithms to essentially remove correlations. And here's the theorem that captures the guarantee of Poissonization. So if X is a data set with a random number of entries, and that random number is distributed as Poisson with some mean n, and they're all sampled from some discrete distribution over k elements, where the probabilities of each of the elements are p1, p2, so on to pk. That's what multinomio means. Then the element count of, then each of the elements counts is distributed as a Poisson random variable. But more importantly, so capital P O is Poisson, but more importantly, the element counts are independent. So you go from dependent element counts to independent element counts in Poissonization. That's why it's nice to have a data set with size that's a Poisson random variable. Okay, and so now I can tell you what I lied to you. Instead of transforming n samples from a distribution P to n samples from a product distribution, we'll allow a random number of samples. So we'll transform Poisson of n samples from distribution P to Poisson of n samples from a product distribution. Okay, so now I'm in position to tell you about a final algorithm. So it takes now a Poisson of n size data set X, all drawn independently from this distribution P. Like before, you just apply one-hot encoding, replace every element with its indicator vector, and now you just randomly shuffle every column, and that's it. That's the data transformation algorithm. So just to visually depict this for more visual learners, let's say the Poisson number you drew at random is going to be 5, and the data set you drew miraculously is the same data set from before. This is not just because I couldn't come up with a new data set, and you apply one-hot encoding, you get something that looks like this, right? Just believe me. And now you're going to do random shuffling, right? So you take the first column, you're going to randomly shuffle it. Let's say a 1 appears in the third entry. You do that for the second column, nothing's going to change. You have no 1s, everything is a 0. You just do that for the entire data set. So it looks something like that. And now I claim that the distribution of the columns are independent. And this is because of Poissonization, the number of 1s in each of the columns is now independent because the element counts in the input were independent. But what that means is that now the attributes are independent, and with some extra work, you can also prove that the attribute distributions are exactly what you need them to be. So you can prove that this actually looks like Poisson of n samples from a product distribution. And just intuitively, you can see that like you no longer have this problem where you have a single 1 in every data entry, right? You can have multiple 1s. And so you may ask, why did we do this random shuffling? It's because in a product distribution, all permutations of a column are equiprobable, and random shuffling sort of allows us to enforce that constraint. And so essentially what we've given you a sketch of the proof of is that there exists a data transformation procedure that transforms Poisson of n samples from any distribution P in this class C sub k to Poisson of n samples from a product distribution. Any questions about this?
Can you quickly recap how the Poissonization work again?
Sure. Yeah, so basically if you have a data set that consists of Poisson of n elements, then each of the element counts is now an independent random variable. So you sort of break dependencies that you would have if your data set size was fixed. And
if I start with a data set of size n, support over k elements,
yeah,
how do I just look at the histogram of the count and then
yes,
generate?
Okay. That's exactly right, yeah.
Okay.
Yeah. Any other questions about this? I went a little faster through it than I would have liked. Yeah. Shubhankar? Yeah, that's a good question. There's a reason I chose to talk about this and not the other one. That's where we sort of lose our generality and we have to consider a structured subclass. Essentially, what we do is we just, if you have multiple 1s, we just output a random 1. We just output an index corresponding to a random 1 in our input. But yeah, I won't have time to talk about, I can talk to you about it offline. Yeah. Anything else? Okay. So just to zoom out, I've told you about this data transformation algorithm. And so we get a data set that looks like it was drawn from a product distribution. We apply the private product sampler. We get a sample from a product distribution, and now we need to convert it back. So we do this using a universe transformation algorithm. I'm not going to get into the details of the universe transformation algorithm just for the interest of time. I'm happy to talk about it offline, but just believe me that it works. And so we get an alpha accurate private sampler A for this class C sub k. But from a lower bound that we proved that I didn't have a chance to talk about in detail today, this needs at least k over alpha epsilon samples. Just by like classic reduction, this means that an alpha accurate private product sampler needs at least k over alpha epsilon samples, where k here is the number of attributes. That's like high level overview of the proof. To just conclude, our main contributions were formulating this problem of private sampling, giving tight bounds for several classes of distributions, and sort of relating the sample complexity of private learning and private sampling. And some interesting open problems, do this for other distribution classes. And also I think an interesting problem is like generate multiple samples without like doing the naive thing. So the naive thing is like split your data set, run the sampler in each split separately, but that's not super sample efficient. You could also try to do post-processing. So if you have a distribution, you could just sample from it over and over again, but then you lose in accuracy each time. So do something that's not those two things. Thank you, and I'm happy to take any questions.